The Rankine cycle was named in honour of William Rankine, a Scottish engineer who developed a complete theory of thermal engines. It was his work that led to the process referred to as the Rankine cycle, in his honour. The Rankine cycle describes a closed-loop process involving heat and pressure gradients, where it illustrates the process by which a turbine is powered by a pressurized medium and is a means of driving power generation plants. In a typical Rankine cycle, the pressurized medium is high-temperature steam, limiting the number of useful thermal sources, notably nuclear, coal, and gas power stations. This is where the organic Rankine cycle comes in. The organic Rankine cycle, or ORC, obeys the same principles but uses high-mass organic molecules. These compounds have a lower boiling point temperature than water, permitting a greater array of thermal sources to be used in order to generate useful work. By selecting a suitable organic fluid, an ORC system can produce useful work from geothermal, solar, and waste heat sources. The expanse of thermal sources allows the fluid engine to be applied globally, taking advantage of lower temperatures usually seen as too cool for typical power plants. The fluid engine concept, the principle of the technology, is that a suitable heat source can be used to generate useful electrical power. Here, the heat source supply is represented by the red orbs and the cooler return in blue. The thermal energy is transferred to the fluid engine system via a heat exchanger, referred to as the vaporizer. In the vaporizer, refrigerant is boiled and the resultant pressurized vapor, shown in orange, is supplied to the engine. Work, or energy, is extracted from the pressurized vapor by the engine, producing electricity via the coupled generator. The vapor, in yellow, upon discharge from the engine, has reduced pressure and temperature, but further work must be done on it by the second heat exchanger, or condenser. The condenser utilizes cooling water to change the vapor back into a liquid. Thermal energy transferred to the water is then dissipated in this instance by an air cooler mediated by fans. The cooling loop is adaptable to the operating environment of the fluid engine, where the thermal energy can be used for secondary processes such as space heating, industrial process heating, or with absorption chillers. The green flow represents the liquid refrigerant as it passes from the condenser to the holding tank. From here, it is returned to the vaporizer via the pump, passing through the small heat exchanger, which is acting as a preheater. The process is referred to as a closed-loop system and will continue generating electrical power, provided there is constant thermal source. The design of the entire system focuses on robustness, reliability, and minimal maintenance requirements, where crucial consumable parts are readily available and easily sourced. The applications of the system are designed around the versatility of the fluid engine, and it is therefore the heart of the technology. Market potential. Domestic. The domestic unit is designed to work in unison with a conventional household boiler system, producing useful electrical energy and a consistent hot water supply. The system can utilize gas, oil, or biofuel boilers. Solar domestic. A small power generation unit utilizing solar thermal energy to produce useful electrical power, with a secondary benefit of consistent hot water supply that could be stored for nighttime use or for heating outdoor swimming pools. A hybridized system can be created which incorporates a biofuel boiler, allowing the electrical power and hot water production constantly with minimal operating cost. Commercial domestic. Small to medium power generation units to work in unison with conventional boilers of suitable capacity, producing useful electrical power and consistent hot water supply for healthcare establishments such as care homes and small hospitals, as well as ideal units for incorporation into leisure sites and hotels. Industrial. The industrial systems range from small to large capacity units utilizing hot water, steam, or waste heat as the primary heat source. Large quantity hot water production, as a byproduct of the condensing process, would be ideal for industries that require hot water in their manufacturing processes. Geothermal. The fluid engine is ideal for geothermal applications, with expansive global locations of geothermal potential linked with the variation in thermal well temperatures. Small-scale geothermal applications are suitable for district heating power schemes with the capability of supplying numerous residential properties with electrical power. Medium to large-scale geothermal applications are suitable for isolated or off-grid power generation or as a subsidy to national grid supply for large establishments. Hot water supply is a capability offered across the geothermal market. Gas expansion principle. The gas expansion system is designed around extracting useful work through the process of depressurization. The supply gas is required to go through a throttling effect to reduce the feed pressure at certain stages of distribution. This depressurization makes no use of the energy initially used to pressurize the gas. Further to this, the depressurization causes the gas to cool, thus requiring preheating prior to pressure reduction to avoid potential corrosion of the pipe due to condensate formation. The fluid engine offers a solution to offsetting the preheating process costs and offering a reliable means of powering auxiliary pipeline equipment in isolated locations.